So, so we are back. Yeah, we take our seats. Okay. Before I announce the next speaker, I have a short announcement a sort of reminder. So at 5:20, we start an Astrophysics in Central Asia roundtable. Please don't forget if you're interested in participating in these activities, stay here. So I hope you enjoyed your coffee break. And our next speaker will be our guest from neighboring country, Uzbekistan. His name is Shuhrat Egambirdiyev. He will talk about high energy astrophysical object study at Majdanek Observatory in Uzbekistan. So you're welcome.
Thank you. When I noticed in the program that there is some roundtable discussions about astrophysics in Central Asia, so I decided to start my talk with some short introduction on the historical subject, but this subject has direct relation to the topic of today's conference. And it is well known that in Uzbekistan, as well as in Kazakhstan, the history of astronomy rooted back to the history, very deep history. And I'm sure that in Kazakhstan, as well as in Uzbekistan, there is even archaeological excavations that shows the people in the ancient times has very deep understanding of astronomical events for predicting the agricultural events, to making calendar and so on. But the most important contribution Central Asian scientists made in the Middle Ages is the period so-called Muslim astronomy. And for example, just enough to say about Ulugh Observatory in Samarkand, which was at the 15th century, we could say that it was astronomical capital of the world. But 5 centuries before Ulugh, the center of science and astronomy moved to Khorasan. This is territory of the present Uzbekistan, and they were working 2 very famous encyclopedists like Biruni and even Ibn Sina, it's Avicenna. And a few years ago, one American scientist wrote a book, Frederick Starr, Rediscovering Central Asia, and I would like to show just very interesting citations from his book. In 1998 AD, 2 young men living nearly 200 miles apart in present-day Uzbekistan entered into the correspondence with verbal jousting that would not sound out of place in 21st century. Laboratory they debated 18 questions, several of which resonate strongly even today. And one of the questions they discussed, are there other solar systems out among the stars? They asked, or are we alone in the universe? In Europe, this question was to remain open for another 500 years, but to these 2 men, it seems clear that we are not alone. And a few years ago, German Orientalists discovered one codices of Avicenna, where he gave the description of supernova 1006. The Arabic report about supernova 1006 by Ibn Sina Avicenna, this was published in 2011, and this is interesting that in this book of Avicenna, who is more known in the West as a scientist who are working in the field of medicine, but in the East he is known more like philosopher. In his philosophical book, he gave description of this supernova, and but this supernova was described in the Chinese and Japanese sources. But unlike them, Ibn Sina gave not only variation of the brightness of this object, but also variation of its color, which was very important. Next picture is this is a composite image made to the 1000th anniversary of discovery of this supernova, which is in the history the most powerful supernova ever observed in the Earth. This is combined, including radio X-ray from Chandra Observatory and optical from University of Michigan, 0.9 meter telescope, and many images to show the remnant of this supernova. And now about Majdanek Observatory. Majdanek Observatory in Uzbekistan was found as a result of 10 years site testing campaign organized by Ulugh Astronomical Institute, and it was discovered at the beginning of 70s last century, so it's almost 50 years ago. But when the place was discovered as a very good site, it was occupied by Soviet military people. So until the independence of Uzbekistan on 1991, this observatory was closed for foreigners. But due to the independence, Majdanek becomes open place, and now we are working on the development of international cooperation with many astronomical centers of the world. And Majdanek is involved to many international programs requiring continuous monitoring of celestial objects. And there is two reasons for that. First reason is very good astroclimate conditions. And second is exceptional geographical location. Majdanek, here, next slide shows world map, and you can see this location of Uzbekistan. And Majdanek Observatory, probably the best observatory on the eastern hemisphere of the Earth. But until the middle of 90s, we had no proper instrumentation to study the conditions at this Majdanek mountain. But in middle of 19th, we made agreement with the European South Observatory, which headquarters in Germany, in Garching, and we started to learn the seeing condition. But first figure shows monthly fraction of clear nights. This is solid line is Majdanek, and the fraction of clear nights about 60%. So as good as observatory last year in Chile. And this is dotted lines is a percentage of clear time for Paranal Observatory, which is probably best in the south hemisphere. And in Paranal is 78% of available dark time. But advantage of Majdanek is, for example, it's anti-correlated with southern observatories, and for period from, say, June to the November, we have about 80% of possible clear times at Majdanek Observatory. And the most important parameter is seeing. Seeing is the size of the image of the star in the focus of big telescope, in the focus of this long exposure. So this slide is demonstrating place with some bad seeing, and this is more or less acceptable seeing. And for this, we had measurements with dim instrument, which is now generally accepted as an instrument for site testing. It was developed by people from European South Observatory, and now we constructed same instrument ourselves at Majdanek and made long-term observations. And today, Majdanek is a fourth among the four observatories in the world where we have very intensive measurements, monitoring of measurements of seeing during the many years. This is so-called cumulative seeing. And for example, we can see at Majdanek, for example, in 90% of possible clear times, seeing is better than 1 arcsecond in 90% of cases. So this figure also shows that Majdanek is as good as sites like Paranal, Roca de la Muchachos. This is on Canary Islands, and a little bit better than observatory at Paranal. Median value of seeing about 0.7 arcseconds. And what it means in practice, this is photo, just direct image, received at Majdanek Observatory. This is merging of Russian Soyuz station and US shuttle. And on this direct image, you can see this antenna which is 60 centimeter wide. At this time, the distance to this system was about, not about, it was 440 kilometers. So just on the direct image from Majdanek, we could see the astronaut was out of the station or was inside, because 60 centimeters is too good resolution. And now Majdanek Observatory facilities. We have 6 telescopes. The biggest telescope has 1.5 meter apertures and 1 meter and 460 centimeters telescope, and they are equipped with 5 CCD cameras. And Majdanek we are doing just direct imaging and photometry, but by now we have no observations on infrared and no spectroscopic observations. This is main instrument. It has, of course, its aperture is not big, only 1.5 meter, but this telescope was designed by Moscow State University especially for high resolution observations. So its optics almost diffraction limited by diffraction. And we were provided by good cameras. This camera was provided with the University of Pittsburgh, I think, and this camera this is now in use. This was provided by consortium of Korean universities. And this is, we made automatic guiding system, which allows us to take the images up to with exposure time about half an hour. So next telescope is 1 meter telescope. This is made by Zeiss company, and at the end I will tell you, we signed an agreement with National Astronomical Observatories of China, and this telescope during 2 years was upgraded, and just these days we got the Andor CCD camera from National Astronomical Observatories of China, and this telescope is started to work almost in automated regime. So this is a Director General of this National Observatory. He comes with representative of Academy of Science of China to see what work was done, and it was last year. And sometimes we had problem with power failure at Majdanek Observatory, but now with Chinese, we have built 20 kilowatts solar observatory. So this telescope, which now will work 70% of time for this Chinese program, is fully supported by electricity. And this is RES-4 telescope, which is dedicated to different programs. I will tell you later. And we have Taiwan Automated Telescope. This was first robotic telescope on the territory of Soviet Union. And this telescope was made for the observations on astroseismology. There is 3 telescopes, one installed in Taiwan, another one installed in Canary Islands and in Majdanek. And with 3 this telescope, it is possible to make almost 100% of coverage of astroseismic stars. So main field of scientific research here I mentioned, but I mentioned by red color only the objects which have a relation to high energy astrophysics and to cosmology. I will now make a brief review of our work on these subjects, which made by my colleagues. I'm just director of the observatory, so I will show you the main result we received. But before, I would like to see the timetable for July 27 for this 1.5 meter telescope, AZT22, and we have only, I said, 6 telescopes, but they are all very crowdedly operated every day when we have clear time. So, gravitational lensing system. Today we had already some presentation on this subject, and this project is aimed at precise time delay between gravitational lensing components, system components estimation using international collaborative program on photometry, spectroscopy, and astrometry of selected gravitational lensing systems. And up to now, up to today, more or less reasonable Hubble parameter values have been derived just for 24 gravitational lensing systems. This is about 10% of known perspective system, and it is important to mention that 7 of them were observed during these years at Majdanek Observatory. We are working on this with cooperation with a few institutions. For example, we are cooperating in the Cosmograil program with people from Switzerland, and I don't know why it doesn't work, but so this is, for example, well-known Einstein cross. This is direct image received at Majdanek. Resolution is about 1 arcsecond, and this is after the convolution procedures we have for this and even lensing galaxy, and this is for comparison image received with the Hubble Space Telescope. And when I'm showing it to the public excursion, I say this costs 1 million soms and this maybe cost $1 million. So this is different. And this is just an example gravitational lensing system UN673. Here on the image received from Hubble, there is, you can see even image of lensing galaxy here. And this case is relatively easy because Majdanek sky quality seeing allow to distinguish between to separate between two components. And you can see the time delay between two components in the R band, and the time delay a little bit exaggerated by shifting one light curve relative to another one, but from these two components we got a time delay about 95 plus minus 11 days. And but not all lenses give such a easy separation. For example, this is another lens which is called cloverleaf, and in this case you can see the separation between components of this gravitational lensing is not good because and this so-called dense field. And for these purposes, standard point spread function method cannot be useful, but for this, in our institute by our colleagues was developed another method which called adaptive PCF fitting method, and this method was recently published in Monthly Notices. And using this method, they were analyzed observational data of this gravitational lensing system obtained at Majdanek Observatory during 8 years from 2001 to 2008. And you can see here this zoomed image on our telescope. One is on the big focus mode and the small focus mode, and the crosses shows the position of components which was obtained by this adaptive PFS method. And this is time delay determination for different components of this gravitational lensing system. And next figure shows the light curves of these components, all relative to the one component A. And today, in presentation of Bruce, your presentation was about noise, which like micro lensing and all this factor. Oh, okay, it was Eric's. So here you can see if you use all 4 components, so components D appears to be very noisy due to the micro lensing, and then lower figure shows 3 components without D. So here you can see the light curves, and with taking into account our determination of the time delay, it shows that method works more or less properly. And Next, this is table from the paper of Oguri. This is relatively old, 2007, and you can see the 16 gravitational lensing system were used for determination of Hubble constant, and 3 of them were observed red in Majdanek, and here you can see the average determination 0.7. And in next, this is more recent publication of 15 by Ratna Kumaran et al. So the value of Hubble constant is 68.1 plus minus 59 kilometers second megaparsecs. And here you can see they were used 24 gravitational lensing system. And here I mentioned only lenses which were observed at Majdanek Observatory, and there are 7. So next is blazars. What is blazars? Today we had many these kind of questions, and according to current vision, blazars are thought to be active galactic nuclei with relativistic jets oriented close to the line of sight with Earth. They are associated with supermassive black holes at the center of active giant, very often elliptic galaxy. The special jets orientation explain in general peculiar characteristics of high observed luminosity, very rapid variation, high polarization, etc. And I will show you just a few examples. Okay, before I have to tell you that for detailed study of observational properties of blazars, it is necessary to assemble optical near-infrared millimeter radio light curves and investigate their features and correlations. And in optical band, spectroscopic and polarimetric observations can be added. And we were involved. So in 1997, the Whole Earth Blazar Telescope, an international collaboration of astronauts, organized it for monitoring blazars in optical, near-infrared, and radio bands. And the web network includes about 40 optical telescopes, 3 near-infrared, 8 radio, and sub-millimeter array. So our institute is involved to web collaboration in 2000, and since that time they were observed more than 50 blazars and identified the fast optical brightness of 4 of them. But hopefully blazars in opticals are bright enough so we can not use 1.5 meter telescope, which is very crowded for other programs. We use 60 centimeters size telescope, this one, and observe the in frame of Follows Blazar telescope on this 60 centimeter telescope. And this is list of blazars observed at Majdanek in 2017. And here is example of blazar variability which was discovered at Majdanek Observatory. These results published in Astronomy and Astrophysics. You can see here that total number of points is 2046, and 80% of this data were received at Majdanek Observatory, and we also discovered this. And next shows just the okay. This is one of the telegram. We discovered brightness variation, optical brightening of 4 blazars during this time. And just last example, this is optical outburst of CTA 102 blazar in 2016. It was called snake-like variation of jet, and you can see that at the end of 16, it reached maximum of about 11 magnitude. This is probably the most brightest blazar ever observed by now. Majdanek is a blue one. This is blue one, is Majdanek data. And The period of relatively low activity was recently been interrupted by sudden rise and with jump to 6 or 7 magnitude with respect to the minimum in the optical and near-infrared bands. The peak of the outburst was observed in December 28 with an air band magnitude of about 11. This event represents the most luminous optical blazar state ever detected, as I said. And this was the recent unprecedented optical outburst supposed the picture of inhomogeneous snaking jet, where photons of different frequencies come from different regions with different and variable viewing angle. This is likely caused by magnetohydrodynamic instabilities developing inside the jet, but it can also be due to phenomena such as jet precession or orbital motion in binary black hole system. This result was recently accepted by Nature just 2 weeks ago. But I have to tell frankly, now I have some young people, I would like to involve them to interpretation. So observation is a different business. So how to make observation, make this stable, take care of the instrumentation, to determine the noise and so on, and extract the data, make some fitting to determine the precise magnitude, so on. But because we have each paper published in 25, 30 authors, it's of course good, but my purpose is to involve young people not only to this observational part, but also to modeling and analyzing this data. So next, gamma ray burst afterglow, which we observed at Majdanek Observatory. And I would like to start this from, this is already, today we say many times what it means, so I will not speak about this. And gamma ray burst collaboration, it's, I could say, the collaboration of the former Soviet Union observatories. It's headquarters of this collaboration is located in Institute of Space Research in Moscow, IKI, and there is 5 telescopes: Shine telescope in Crimea, Majdanek telescope, and the telescope of ISON. This is more or less amateurs company, and SEIS in Caucasus, and this telescope on Russian observatory in Siberia, Mondi. And I would like to show you some statistics. So statistics of observation in 2003-2017. We were involved to this program in 2003. As you can see here, we showed number of bursts, then total net exposure, and yellow number of publications, but I can show you this is in numbers too. So during all this period was observed 143 gamma ray bursts and transients, and 73 afterglow was detected. There is a number of publications and in circulars, including in gamma ray burst coordinated network circulars, and in a reference journal, 26 publications in this collaboration. And this is just Majdanek? Majdanek, yes. Okay. So, net total exposure per year, 24 hours. And the gamma ray burst per year, about 9. And mean delay since gamma ray burst trigger is 6 hours, which is very bad from point of view what you tell us before. But this statistic for the 14 years, and we have internet at Majdanek, I think, starting 2009. But before, we got the information by telephone, and it was very complicated. So this is why maybe I have to separate it on 2 parts, before internet and after. But now still we cannot do a few minutes, but it comes to 1 hour about, maybe a little. So, and this is, I would like to show as an example monitoring of gamma rays burst 130702, which started with Majdanek 1.5 meter telescope on July 3, 2013, 1.5 days after Fermi trigger of this object. And this is second gamma ray burst, which is associated with supernova after the supernova of 98 you mentioned today. And so this is log of our observations, and you can see this is like color. It is all observations made in Majdanek. Again, it's very crowded. And this is modeling of multicolor light curves of this supernova associated gamma rays bars. And this consists of 320 photometric points, and 25 of them are obtained at 1.5 meter of Majdanek, observed in filters B and R. And there is also some data taken from publications. And next conclusion is we obtained the pre-supernova star mass, about 25 solar mass. The mass of resulting compact remnant is 6 solar mass. The total mass of the ejecta was estimated about 19 solar mass. The large ejecta mass and the possible presence of clumps of matter around the progenitor are consistent with the explosion of rise of massive star and suggest that the progenitor was a massive Wolf-Rayet stars, and ejecta expose a wide draft companion and initiates the type 1A supernova explosion. And we are doing with the consortium of Korean universities, which provided us the CCD, with the intense monitoring nearby bright galaxies. The primary aim of this project is to study the early time light curves of supernova, since such data on supernova can teach us a great deal about the structure of progenitor stars. And again, as an example, I can show you the very recent discovery of supernova 2017 EIN at Majdanek Observatory. So you can see here, this is a galaxy and NJC 3938, and there is no supernova here on 23rd of May, and on the 25th of May, we can see here supernova. And this is supernovas under study. And next figure shows the Ursa Major constellation, which covers 1,280 square degrees in sky, ranking the third in size. And this is well known constellation, and the supernova was detected here. Of course, we were very lucky that on the time when it was appeared, our telescope looking to this point, because we have about 70 galaxies, and each night we observe up to the 10, and it was good luck to see this. And this is very recent light curves, which I get from my guys. This is until the July 24, it's 2 weeks ago. So this is a date when supernova was discovered. This is observations at Majdanek 1 hour before the date will change to 26. And this is sensitivity of the Majdanek data. This is observatory in Korea, and you can see the light curve of the supernova, very crowded again, Majdanek's data. And now this process is continued. And what we can say now, by now, that is an unbarred spiral galaxy constellation. It was discovered by Herschel in 1788, but up to now, they were detected 4 supernova in this galaxy. So this, indeed, it is very active on appearing a supernova.
Sorry. I think the batteries are discharged. Could you use this mic? Thank you. Yeah.
And this is, I told you about, this is, has no relation to the high energy astrophysics, but in 2014 we have signed an agreement with National Astronomical Observatory, Chinese Academy of Science. They proposed the program Stellar Abundance and Galaxy Evolution. They developed this very new photometric system which is extremely powerful and sensitive to the atmospheric parameters like effective temperature, gravity, and metallicity. And we started to work on this program just these days because new CCD was installed. And we plan completeness of such survey is we could reach 19 magnitude in V band, detecting about 500 million stars in 5 years. This would be very good participation of Maidanakas. And last point I would like to say in a few minutes about astronomical education. Astronomy in Uzbekistan taught in 5 universities and in 4 pedagogical institutes, and up to recently, until 2006, there were no one astronomical educational observatory. So during the 8 years, Astronomical Institute of Uzbekistan, almost without funding, with zero, very close to zero funding, we built 6 observatories for our universities. And this is 48 centimeter Grab Parsons telescope installed in Samarkand University. And we made this very interesting work with students of the Samarkand University because it was program of observation of Delta Scuti stars. And we found that this stars is analyzing of light curves shows that this is stars, in fact, a closed binary system with period about 6.1 days. It was not, so this was done by the students of Samarkand University, and this is observatory of Andijan University. You can see everything done just simply by ourselves. This is all telescope which were installed in Majdanak and which are not in use. We repaired it and installed it there. This is a famous place, solar furnace, which was installed in not far from Tashkent. But this is like a solar oven which was installed in south of France by NATO. Okay, I'm just finishing. And this is AZT-14 telescope for observations of the students of National University of Uzbekistan. It's 48 centimeter telescope, so we are working also on teaching students. I think this is all. Thank you for your attention.
Thank you for the nice talk. So are there any questions? So there were some few questions during the talk. So okay, then okay, good.
Very small question. What relations you have with our Kazakhstani astronomers?
Okay, this is very good questions. We have cooperation with about 25 institutes of the world, and we have zero cooperation with Kazakhstan astronomers. Zero, yes. But except sometimes when we have dissertations, your people come to us, and so. But we have no common program, and which is very bad, because. So we have to develop it. This is, I understand. Maybe we can about round table discuss this.
In fact, I'm surprised that you have a gamma ray burst follow-up program, and at Tian Shan they have a gamma ray burst follow-up program. You both produce GCN circulars.
Know it.
And you know, why don't you guys get together and double the coverage?
Yes.
So any more questions? Okay, good. You have a mic.
So first, let me please. Let me say that I think this is very exciting, and let me say that I wish I had a site with good seeing like yours. But now I'm going to ask you some very hard questions, and I hope you understand that these are not meant to insult you, but just to be very hard questions. And the first most important question for me is, how is the internet at Majdanak?
Now we have internet by through the telephone line with modems. But now, in a few months, we are having plans to install the real satellite via satellite internet. So my internet should be very good very soon.
Test 1, 2. So soon satellite, but no fiber optic.
No fiber optic, yes.
Okay.
Yet.
Okay. And again, more practical questions. Is there a cloud sensor that broadcasts to all the instruments on site by internet?
Yes, we can get, and now we have a good fisheye camera, which we can detect the cloud situation.
So, are you happy with the answer? Okay, good. So then, if there are no questions, thank you again. So our next speaker is a PhD student who is in his final year. So his name is Iran Aymuratov. So you're welcome, please.
Hello. Today I'll talk about short gamma ray burst. Professor Grossen was mentioning the long one. I will stop a bit on the short. And the output of my work, first, I will do mostly the phenomenological approach and give a small motivation for that. Then we'll introduce the fire shell model of the GRB, of gamma ray burst, then proving by the prototype burst 090227B, then give a small results on the X-ray and the GeV emission of the short gamma ray bursts and outline particular last results on the 081024B and 1404A GRB. Okay, what we can do with the GRBs is mostly the phenomenology, and the brightest example of the phenomenology is the B-model distribution obtained in early 90s by the Batzer. What you can see, the distribution of the duration of the GRBs is B-model, so it's separated into the short one and the long duration gamma ray burst. The typical short gamma ray burst looks like single or highly structured spike with a duration of fraction of seconds, sometimes milliseconds, and in compared to the long one, which is kind of 20 to 40 in average, we have a very little result and very little information on the short gamma ray burst. Apart that by phenomenological approach, we could say that the hardness ratio, the ratio of the different bands of detection, tells us that the short GRBs are mostly hard spectrum than the long one. So motivating by this, we could do a little bit more research, and this is another example of the phenomenology. What we could see that the E peak of the spectrum for the GRB, for the long duration GRB with the known redshift, it's again thanks to the optical observation of the ground-based telescopes. The diagram of the E peak versus the isotropical energy shows us that the long duration GRB follows the common behavior. This paper was obtained by Amati for 41 GRBs, and then recently it was extended for the since more data was available with the redshift. Apart that, as I said, the very fast, very frequent and rapid short GRBs are very hard to catch. Then it's very hard to point the optical telescopes and even the X-ray telescopes and obtain the redshift, measure the distances, and obtain values of the estimating the energy and the. Okay, for the peak energy we have some information but for the isotropical total energy we have no clue. apart for several few examples. Which is more rare, we could not obtain the GeV emission, high energy emission more than 10 MeV from the short gamma ray burst. And this is causing a big problem of understanding the general scenario and progenitors of the GRB. For the moment, we could say that the long GRBs as a progenitor has the collapsar or supernovae falling gravitationally into a big collapse and then starting with the expansion. But there are also two scenarios: forming a black hole or not forming a black hole with a magnetar, highly magnetized magnetar. But for the short GRBs, up to the moment we have several guesses, and one of them are merging neutron stars, black hole neutron star, or black hole, which is currently going to the fashion. Let's do a little bit phenomenology with this distribution of the short GRBs. They're also following the line of behavior, but we could say there is a very famous, very bright 09 or 510 GRB, which has the GeV emission, high energy emission. Rest of the short GRBs has not. And we were very curious why statistically, let's say, more observed GRBs has no. So there could be some underlying physics, and we give as a benchmark energy of 10 to 52 erg, and let's try to explore this part of the graph, of the diagram. Recently we derived, with the help of the fire shell model, I should mention that the fire shell model is not the mainstream, and recently we derived that this GRB 090227b has is lying on the line with the energy more than 10 to 52. So we need to check for the several points, and the main point we should check either it has a GeV emission, which is actually was not observed because of the time delay of the machine on the satellite. So for that we need to introduce a little bit of theory, and the fire shell model outline is saying that we have a electromagnetic black hole, Kerr-Neumann black hole, and during the formation of the black hole, the electron-positron plasma is expanding. It has initial total energy pumping in a sphere, and that sphere is expanding freely with a and going to the relativistic speeds. On the way of expanding, it interacts with the baryonic matter, which is either the remnant or the circumstellar circumburst medium. And slowing down, it interacts and it is heating up until the radius of the transparency with the scattering of the photons is not the transparency value is equal to 1, and the photon are able to escape, and we see the first light. I should notice that before we don't see, so this is kind of a theory, and it needs a more deeper investigation. But again, from the point of transparency, we see the first light. Then it goes further and interacts further to the point of total deceleration, and then we see the outshine in the X-ray, optical, and radio bands. So this is the diagram of the Lorentz factor. As I mentioned, it goes to the relativistic values, then the first interaction with the baryon till it goes to the transparency point, to the constant Lorentz factor. It propagates, and then it interacts with the material of the surrounding. So the main values we need are the baryon load. The material is going around the black hole or whatever is in the center, and the ratio is called effective area, which is needed to calculate the main properties of the observed data. So here is the lines of the main characteristics of the expanding plasma for different energetics, initial energetics we have, and by the structure. Okay, we are going back to the E-peak-E-ISO relation, and by the structure and investigating of several years, the so-called nomenclature of the fire shell model is now presented by the short gamma ray burst, and that's called short gamma ray flashes with the energy not enough to produce a gamma ray GeV emission. Another type of the long GRBs is out of my scope, but I will mention several words also. This is the main complicated a bit structure of the outline of the fire shell model. And here we'll focus on this part, on this branch. And we could say that the main features is the not forming of a supernova, like in a case of the long GRBs, but forming a black hole with the hard spectrum, which is indeed so. X-ray, we believe that there is an X-ray afterglow. As an example, there is one observation of 090510, and we state that there is a GeV emission of every short gamma ray burst. Also, we give some estimate for the rate of observation in a visible universe with modern telescopes. So, to the moment, we have 5 short GRBs with the GeV emission. One of them is really observed with a redshift, and everything is known and calculated very well. Especially because of that GRB, we have the full line, and we can do the upper limits and calculate the others and see if it's consistent with the data and analysis done within the fire shell model. Today I'll focus on 4 of them. Okay, unfortunately 090227 is not written, but it's here and it's within the 3 sigma upper limit. So as you see, the evolution of the progenitor tells us if there is a supernova formation, and the main point of the fire shell model is that all the GRB is produced as a progenitor with a binary system. Either a neutron star with a supernovae, or the black hole with a neutron star, or other configuration of that tree. But in the end, because of the energetics of the forming black hole, there is anyway should be accretion, and that accretion is forming the GeV emission, we believe. In general model evolution, there is X-ray formation because of the interaction with the circumburst medium. And this branch tells us that the prototype, this is the real analysis of the data analysis which should be done to step by step, and I will show that single peak or highly structured peak of the short GRB should be divided in 2 parts. And in 90% of the short GRBs, there are really 2 parts which could be separated in 2. And according to the structural analysis, we could say that there is some underlying physics. With the analysis of the first part, which is called the proper GRB for the cleavage, we could extract, we have the flux of the arriving flux, and we could extract the value of the total energy by calculating the equation of the isotropical energy. And by simulation and the procedure of trial and errors, we could get a value of the baryonic matter forming around that black hole. And then, because of that, we could calculate the Lorentz factor of expanding and the transparency radius at which the first light was emitted. Then there is a second part. We say that it's mostly because of the interaction of the circumburst medium with an expanding plasma. And it could be combining effect of the 2 fitting of the two fitting model fitting. Here we use two detectors to increase the statistics. And mostly focusing on the second part, we simulate the visible light curve and get the values of the circumburst medium density. And simulating further the density, we could get accordance, we could check for the accordance with the spectrum, within the spectrum. And here the red solid line is the simulation, and the green and the blue dots with error bars are the data of the two detectors, which is working from 8 to 40 from 8 keV to 40 MeV. So we have the measured GRB, and we say that it is in the consistence, and there is a theoretically derived redshift. Within that theoretical redshift, it goes to the energy, which is slightly above the energetic 090510. But we still need to check for the GeV emission. We do it further, and I will show you that because of the instrumental effect, Swift satellite was entering the field of view of that GRB too late, around 900 seconds. But the analysis we do is saying that there is an upper limit, and it was just before the Swift XRT was entering. Another example, we were growing the statistics of that short GRBs, and another GRB 140619B was done the same fashion. We have the first pulse, the second pulse. We have the fitting results giving us the peak energy and the fluxes with what we could calculate the parameters. And here we say that that the fraction of the first spike to the total duration of the spike is 40%. So you could see here that is 40% of the emission comes from the first slide, and the rest part is somehow 60% with the interacting with the baryon. And doing the same procedure, we could get the density profile of the expanding with what the expanding the shell will interact, and get the spectrum. So we could model, we could put this GRB with energetics. It is also consistent. And for the GeV emission, we just simply built a luminosity versus the luminosity evolution with time. And here is the upper limit for 090227B. Further, we will show that the main well-observed GRB with lying on the line, and it's consistent with the assumption we do for the short GRBs. And as I said before, for the family 1 less energetic GRB, there is no Jeff emission, and it should lead to the signature that there is underlying physics. And several years ago, Professor Kumar said that there is a correlation between GeV emission of the high energy emission of the GRB with the X-ray afterglow. And indeed, there is a correlation in the power law slope. But for the short GRBs, we don't have any X-ray afterglow. So here we compare with the long GRBs, and it's still consistent, especially after the time 10 to 4, 10 to 5. It goes to straight line and have the same behavior. This work is done in our group and extended to the sample of 161 GRBs, and it goes to the straight line of the power law slope with an assumption of the jet with a maximum angle of 17 degrees. So not only the X-ray part, X-ray afterglow goes to the behavior, but also the optical. But this is out of my scope. Then we should ask why they're so different. They're the same short GRBs, but ones of them don't have the GeV emission, and there should be some physics. And we state that there is a black hole formation which is causing the accretion, and the GeV emission is occurring. So here you could see that there is no GeV emission, and all of these GRBs show the high energy emission signature. Again, we grow the statistics, and this recent two GRBs, the results of this recent two GRBs was going to the publication, and confirms the assumption, the suppose we did about the short GRB emission. So here the standard procedure, as I said, we use the data of the Fermi, which is more which covers the more wide energy band from 8 keV to up to GeV. So we have the possibility to catch the GeV photon from the short GRBs. This is the fitting procedure. We get the information on the E peak and the flux with what we could get the main parameters values. So we divide the burst as you see for the first pulse, and another part is the second pulse, the rest one. And there is also notice that GeV emission occurs exactly after the end of the first pulse. This is also very interesting, and this is also pure phenomenology. We could deal with that. And the assumption of the first pulse of different physics, of different origin, is has a right to live also. So there is a small complicated procedure of the redshift estimation based on the ratio of the energetic of the first pulse and the second pulse to the total amount of energy. With the fitting, we could extract the temperature, and with temperature, we could extract the redshift. And based on the redshift, we could extract the value of the energy, which tell us where on the E-peak-E-ISO relation the GRB lies. So this is the self-consistency check. In the end, we check either the E-ISO, which was derived, is consistent with the baryonic load, was assumed, and the total energy of the electron-positron plasma was also taken in that, under the assumption. So, as I said, you could see that the GeV emission starts after the first pulse. Here is very clearly seen, and the GeV photons are lasting longer, much longer than the burst itself. As I said, the short GRB is just 2 seconds at most, and the GeV emission could last also to tens, dozens of seconds. So, especially for this GRB, we did the same procedure of the analyzing of the second prompt part, deriving the density profile of the surrounding medium, and calculated the main values of the radius at which it hits the clouds of the proton clouds, and the values of the Lorentz factor at what it gets after the interaction. And we put these two GRBs, the last two GRBs. Here is the preliminary result, but then it's consistent with the 3 sigma upper limit, and it's still going well. They all have the GeV emission, and they all lie on the same line of the E-peak-E-ISO relation. So we should check for the GeV emission diagram, as I said, and the simple luminosity versus luminosity evolution of the GeV emission tells us that they all also lie on the same line, and they somehow correlate with the X-ray afterglow. Unfortunately, there is no dots of the 090227b, because I said the X-ray telescope was entering the field of view of the very late, 900 seconds after the burst. It was too late to detect it. But then we could get at the upper limits for that and calculate the redshift which is seen here, and all of that redshift is in a well consistency with the general information on the short GRBs. And last information I wanted to say that only this GRB has the X-ray afterglow observed. All of the rest 4 don't have the X-ray follow-up because of the technical and the upper limits of the detection telescope. We simply corrected the data points on the redshift of each GRB to see if it goes well, and we see that this black arrow is the time when the XRT starts its observation, and we see that light curve goes well below, and it's below the threshold of detection here, and for this there is no observation at all. So we could say that at high significance, all the GRBs could have the X-ray afterglow, but because of the technical and the upper limits, we don't see. Maybe it's a deal of the future observation, and we need to grow the statistics. So this is a small conclusion I get, and I again want to say that not all short GRBs are able to produce the GeV, but that who is producing it with within a relativistic jet, and they calculated in the XRT afterglow. The angle of the relativistic jet is consistent and within this 17 degrees. So, but if we don't know the afterglow, and the afterglow is not observed, we could still derive the main values and estimate the physical parameters as the total energy and the baryonic load of the circumburst medium, which could give us seed to further theory and modeling. So thank you for your attention.
Okay. So thank you, Ilan. So we have time only for a few questions, if somebody has one. So, okay, good. Yeah.
Just to make clear,
Yes.
you mentioned that not all short GRBs produce GeV emission.
Yes.
The same is also true for long GRBs. Not all long GRBs produce GeV emission, only a fraction of them do. So, coming to the question now, the short GRBs from which you do not see GeV emission, are they lower luminosity GRBs with no GeV emission?
Yes.
Or
They are somehow failing from the formation of the black hole. So they have a less energy to form a black hole, and that black hole is the main point to do accretion and produce a GeV emission. At least we suppose that this is how it's going.
Actually, my question was really more of an observational question. I was not going into the theoretical side of things, which we can talk separately.
Yes.
I think it would be not appropriate to talk about it here. Just observationally.
I could say that observationally,
short GRBs with no GeV emission, are they fainter, have lower luminosity
yes.
than short GRBs with light emission?
Yes.
That's just my.
They are. They are.
They are.
You see that the peak energy
entirely consistent with the behavior that is seen for the long GRB.
Yes, you could see that the benchmark of the 10 to 52 ERG is well correlating also for the long GRBs, because for the long GRBs we also has stated that there is a formation of the black hole, and here is not. And because of the formation of the black hole, we have enough energy, and we have the remnant mass to accrete, to interact and produce the GeV emission. This sample of 161 GRB is well analyzed, And I could show you. So here's the first 7, and it's seen that after 10 to 4 in the X-ray, they have the same behavior. This is a large sample of 161 GRB, and after 10 to 4, we could say that they follow, but we are not sure. But when we introduce the beaming, that simple equation of beaming, it narrows, and it means that there is a connection and correlation with the X-ray, beaming, and the GeV emission. Here, all that 161 GRB has the GeV emission. So the energy is enough.
That is consistent with what we had predicted.
Yes, this is consistent.
Okay, so I think we're done for the question session. So let's thank Yerlan again. So thank you. So, and please welcome our next speaker, who is a professor at Nazarbayev University School of Science and Technology. So Yernazar Avdikamalov. Okay. So.
Как?
So I remind you that the talk will be like 20 minutes around, and plus 5 minutes for the question session. Thank you.
Thank you very much. Thanks to organizers for giving me an opportunity to present this talk. So my name is Yernazar Avdikamalov. I'm an assistant professor in the physics department of Nazarbayev University. I will talk about the explosion mechanisms of core collapse supernova. In other words, my talk is about how massive stars explode, how they start exploding. Throughout my talk, I'll be mentioning a lot turbulence. And that's because in the last few years, it became clear that turbulence was a missing link in producing explosions of massive stars. Okay, so this is a project I started a few years ago when I was back at Caltech, and I moved here, and we are continuing this topic here together with our students. In particular, I would like to mention Shapagat Berdebek, who is our first PhD student in our department, Tanat Issa, who is a third-year student who is now today in Princeton working with Adam Burrows and doing some spectacular job, plus finally Azamat Shahsilikov, who just graduated and who moved to continue as a PhD in the University of Wisconsin-Madison. And these are my international collaborators. Okay, so why we are interested in core collapse supernovae? Core collapse supernovae are very powerful explosions of massive stars that happens roughly once per galaxy, and it lasts for weeks, and it emits as much energy as the sun during these weeks, as sun emits through its entire life. So why it is interesting? It is interesting because core collapse supernova produces most heavy elements than heavier than iron. So it's very important for galaxy chemical evolution. Core collapse supernova produce black holes, neutron stars. They are connected to gamma ray bursts. So in other words, core collapse supernova are central engines of gamma ray bursts. And they emit gravitational waves and neutrinos, which is very interesting, which makes them very interesting because through gravitational waves and neutrinos, we can see the inner parts of the systems, which we cannot see otherwise. Only neutrinos and gravitational wave signal allows us read direct information from the center of these objects, through which we can probe fundamental theories like nuclear physics or probe some astrophysics like stellar evolution. Okay, so how does core collapse supernovae occur? It occurs in stars which are more massive than 8 times mass of the sun. In those stars, at the beginning, of course, like with every star, we start with a hydrogen. Hydrogen burns thermonuclearly, step by step, and at the end, it starts producing iron. Iron is a special element because it has the highest binding nuclear energy, which means you cannot burn iron and produce something else. That's why iron core accumulates, becomes bigger and bigger. It cannot grow forever, however. At some point, it reaches its maximum mass, 1.4 times mass of the sun, at which point iron core becomes unstable and collapses to a neutron star. And that emits huge amount of energy, and part of that energy should be used to produce explosion. That we know for sure. It should use part of that release of potential binding energy to produce explosion. How exactly that happens is unknown. That's the topic of my research. Okay, so what are the ideas which we have? Depending on how much rotation we have, there can be completely different mechanism operating. So when we have slow rotation or when we have rapid rotation, we have completely two different mechanisms. When we have slow rotation, we have known what is called as neutrino mechanism. Neutron star, which is just formed, is very hot, emits a lot of neutrinos, and some of these neutrinos push a shock wave, which is supposed to produce explosion, and energize it, and ultimately produces explosion. So that's a neutrino mechanism. Second mechanism, when you have rapid rotation, is so-called magnetorotational mechanism. Magnetorotational mechanism acts in the following way. We have a neutron star at the center here, rotates very rapidly. It has a lot of energy, maximum of around 10 to the 52 ergs. And that energy, according to this mechanism, is transferred through these magnetic fields, outer parts of the star towards outer parts of the star, which is ejected. And people believe that this mechanism, through this mechanism, we can produce the most powerful explosions known as hypernovae, which are connected to gamma ray bursts, which Bruce mentioned before. Okay, throughout my talk though, I will talk only about the neutrino mechanism. Okay, so neutrino mechanism. So iron core collapses to a neutron star, forms a shock wave starts expanding, and on top of that is neutron star, which just formed. This is a shock, this is a neutron star. Neutron star is roughly around 15 kilometers in radius. Shock is at some point becomes around 100 kilometers radius. Some of these neutrinos emitted by neutron star are absorbed in this region behind the shock. Those neutrinos deposit their energy, heat this material behind the shock, provide additional pressure, and hopefully that will energize the explosion. All right, that's the idea. Let's see what happens. Let's try to simulate this process in 1 dimension assuming spherical symmetry. Let's see what happens. So this is an animation which includes all the state-of-the-art physics which we think are important here. So this is a infall velocity, radius. This is a shock just formed. Shock is propagating outwards, but it doesn't propagate outwards and stalls at a radius of around 80 kilometers. Okay? So this is what happens when you include all the state-of-the-art physics, which we think is important, and we do simulations in 1D, assuming spherical symmetry. So what's going on? What's going on here? What's wrong here? What's wrong with this simulation? The answer is, of course, the assumption which we made, which is we are assuming spherical symmetry, turns out to be completely wrong. So people started doing 2D axisymmetric simulations starting around 90s, but then in the last few years, people realized that 2D simulations are completely wrong because, as I will show later, turbulence is not captured well in 2-dimensional simulations. So around 2010, people started doing 3-dimensional simulations of core collapse supernovae. We were one of the first to do such simulations in 3 dimensions, and I'm going to show an example of such simulation. So this is a shock wave. This is a neutron star. It is evolving. Shock is not very energetic. It is just staying there as an accretion shock, like in our 1D model. But what is changing here now compared to that 1D model is because in this region now, we are having some convective motion. We are having buoyancy-driven convective turbulence, in other words. It's a turbulent motion. So that turbulence model, as a turbulence motion, it turns out, energizes a shock, and the shock starts slowly propagating outwards, as you can already see here. So why shock is more energetic when you have turbulence? That's very simple to understand. When you have turbulence, suppose this wall is a shock. Okay, suppose this wall is a shock. And suppose we have turbulence right here. What happens is that this turbulent motion, this chaotic motion of the air here, will hit this shock and provide additional pressure, and that will energize the shock. It turns out that is key. Okay, all right. So what happens? What happens if you do 3-dimensional simulations? So this simulation is, in a sense, fake. Why? Because here we are artificially increasing neutrino heating. We have more neutrino heating than realistic. If you put realistic neutrino heating, it turns out it doesn't explode again. So what is missing here? Sorry. So what is missing? It turns out we forgot something which is really fundamental. So let's look at a stellar model just before collapse. just before the collapse of the iron core. So in this stellar model, the silicon shell, which is just outside of the iron core, and oxygen shell, which is just outside of it, is still burning. There is a lot of convection going on in these areas, in these shells. But in our simulations, the mistake which we are making for the last 40 years was that we just took 1D stellar evolution models from stellar evolution codes, and that was the biggest mistake. That was a big mistake. So in the last few years, people managed to do 3-dimensional stellar evolution simulations. It is very expensive, so people can afford simulating only the last few minutes of stars just before collapse. And for the first time, it was achieved by Sean Couch in 2015. So here, this plot shows the iron core. This is iron core. This is silicon shell. This shell is silicon shell. It's a shell which is burning silicon. And we see a lot of convection in this region. And that convection, when it hits the shock, it turns out has some non-trivial effect. And this was seen in the simulations by Müller et al. Just a few months ago. So let's look at this plot. This plot shows a radius of the shock as a function of time. Okay, this is time, this is the shock radius, this upper panel. So we have few lines here. This black line is what happens when we start from spherical symmetric stellar evolution models, which do not include that convection in the silicon shell. If we include that, this is what happens. This is a red line. If we include that, star explodes very fast. If we include half of it, artificially reduce that convection, we get this blue line. So something in between what we get from spherical symmetric models and full 3D models. Okay, this is very nice. This is very nice. But the question is, what is going on here? What exactly is going on here? These simulations become so complicated that we don't even now can identify basic physics which is going on. And that's the purpose of the project which we are doing now, to understand the physics, the simple physics of what is going on in simulations. Okay, so this is a project which we started around 2 years ago. And what we want to do here, our ultimate goal is the following. So this is my attempt to draw this silicon shell, which looks kind of awful. So this is our silicon shell. So we have this turbulence here, and this is my shock. This is my stalled shock. I want to re-energize it. So I want to understand, we want to understand through only linear physics, how these perturbations evolve as they are occurring towards the shock, what happens when they cross the shock, and how it affects post-shock flow. That's what we want to understand. That's the main topic of our research here. Okay, so we made some good progress together with the students on this second part. What happens at shock crossing? What happens to turbulence when it is crossing the shock? And that's what we're going to discuss next, okay? So we take very simple model because we want to understand the physics. And sometimes the simpler the model, the more physics you understand. So this is my shock wave, and I have this turbulent flow. I want to cross this shock wave. We will use a model which was developed in the 50s in the aerodynamics industry. It is called linear interaction analysis. People developed this model in order to understand noise generation in supersonic jets. We are going to use that to study stellar explosion. Okay, so it's a linear perturbation theory. We have mean flow plus perturbation. So it's on one side, we have again mean flow, this part, plus perturbations. So we relate these two, and we understand how turbulence changes from one side to another. Okay, so when this is valid, this is linear theory. Is it valid? Can we use that? It turns out yes. In aerodynamics community, this theory has been tested in detail extensively, and they come up with this empirical relation where this theory is applicable. And it turns out in the context of purple supernova, this condition works beautifully. So we can use this theory. Okay, we want to, that's still a bit too complicated for us. We want to make it even simpler. Okay, so how we can do that? Here, I have these linear perturbations. I have perturbation of velocity, I have perturbation of pressure, I have perturbation of density, and so on and so on. But the values of these perturbations, to which physical modes they correspond to, I don't know. Yet I don't know. I want to decompose, in other words, turbulence into its physical modes. Any hydrodynamic turbulence has three components, it turns out. It has so-called entropy modes, vorticity modes, and acoustic modes. We split them into these three components, and there is a beautiful result which shows that those modes in the linear regime evolve independently. Shock turbulence interaction in the linear regime for all these modes are completely independent, which means we can study for one mode, for the next mode, and so on, and then integrate the result. Okay, so there are three modes: entropy, vorticity, and acoustic. So we naively opened Landau-Lifshitz hydrodynamics book, and we looked at what are the amplitudes of sound waves in turbulence. And we found this relationship which says sound energy in the sound waves in turbulence is proportional to Mach square to the power 8. So we have subsonic turbulence, which means Mach number is smaller than 1. So smaller than 1 to the power 8, forget about it, we thought, naively. How wrong we were. Okay, so we're using this argument. We just included entropy and vorticity waves. We calculated how exactly these waves cross the shock and amplification of turbulence through the shock crossing. And we came up with this, for example, among other things, we came up with this estimate. We found that critical luminosity for producing explosion, critical neutrino luminosity for producing explosion, decreases by around 12% when you have these kind of perturbations. That's exactly in line with what people are finding in simulations. So here we have some really nice, really simple explanation of what is going on in these simulations. But this is not the end of the story. Regarding this acoustic wave, as I said, we were very naive, and I will explain why we were very naive. This is the result which has been known in the aerodynamics industry for decades. When you have a converging flow, for example, here we have a converging flow, everything is converging. If in that flow you have, for example, entropy perturbation or vorticity perturbations, if those perturbations are advected towards the center, towards a higher density region, that emits a lot of acoustic waves. Okay, when these guys are accreting, initially there are no acoustic waves according to that result, but when they are accreting, that emits a lot of sound waves. That can be shown very easily. Basically, if your perturbation moves from a region with enthalpy H2 to a region enthalpy H1, if that region has a mass of delta M, this is the energy in acoustic waves that is emitted. Okay, so we are working on this together with students here, and hopefully soon, in a few months, we'll have a paper which also takes into account the effect of acoustic waves. After that, we'll have to see what happens to the post-shock flow. Okay, I'll stop here. Thank you very much for your attention. I finished. Okay.
Interesting to see the effect of the acoustic waves that is produced by turbulence. And indeed, the well-known result that you mentioned from Lighthill and so on.
Yeah, exactly.
Scaling as Mach number to the power 8.
Yes.
But there is another kind of wave which is also generated by turbulence. And that is internal gravity waves, which has a much weaker dependence on Mach number.
Yes,
so long as you are considering a system which has got Mach number of order unity or maybe a little less. And the system I think you are considering has a Mach number which is a little less than 1, right?
It is less than 1, it's 0.1 probably.
Oh, yes, right. So you see, so that makes a huge difference because the amount of energy luminosity carried by gravity wave is much larger when you are considering Mach number of 0.1.
I totally agree.
That dependence, the luminosity carried by gravity waves is, I forget, I think it's maybe Mach number squared. So there is a much larger luminosity carried by gravity waves. And I wonder if you have looked into it or looked to see what the effect might be.
Yes, that's a very good question. I totally agree with everything you said. And the simulations do see emission of gravity waves. And we also did some basic order of magnitude estimates. They do exist. They are noticeable. You can see them. And they have, I would say, a few percent effect on the shock dynamics for the parameters which we used. So that's all I can say right now. Maybe there are parameters for which it's stronger or less strong, but that's what I know as of now. Actually, we have an appendix in one of these upcoming papers where we exactly make order of magnitude estimate for that. So we find it to be a few percent effect, not dominant.
bit surprising, but I'm sure that you have got it right.
Yeah.
My intuition, based on my estimate, it seems that it should be a larger effect.
Okay.
But
So
as I say,
yes.
this
So
is something I'm sure you have done
yeah.
the correct calculation. So
Yeah, we have. I mean, we have simulations, and we have also order of magnitude estimates, analytical estimates. Both of those results roughly agree with each other. It's an effect, so it's I would say a few percent effect, at least for the models which we consider. But again, stellar models have very wide range of varieties of parameters. Maybe you are totally right. Maybe for some parameters it will be a really strong effect, and I would be very curious to see to look at it in more detail.
can I just ask one very quick follow-up question?
Yes.
And that is the presence of the turbulence.
Mhm.
Does that I missed that point.
Mhm.
Is it enhancing the neutrino energy deposited in the shock front or
Okay.
not?
That's a very good question. So, so what is happening is, I think now people agree that I mean, it's not fully resolved issue, but I think the most dominant effect of turbulence is the following two. First was this additional pressure, this turbulence stress, right? If you have this, that's fine. That's one effect. That's probably roughly maybe 20%, maybe no, some significant fraction of the total turbulence effect. Second part also, this guy, this turbulent motion decays, right? Turbulent decays, constantly decays, and that decays hits this region, right? Additionally, and some people think that that's actually the dominant effect. So hitting under this push are these, I would say, two dominant effects here.
But the heating is a small effect again because the Mach number is 0.1.
Mm-hmm.
So the amount of energy that is added to the system
Mm-hmm.
due to the heating of the turbulence
Yeah.
is roughly 1% of the thermal energy. And so
Well,
I would be surprised that it has a much larger effect.
so this result actually came out. This result came out a few weeks ago by
You have the same question.
by a group in Florida, by Jeremy and Murphy, and they made this simple steady state models of 1D models, and they looked at effects of different terms, and they found that that heating for the somewhat realistic models of Krakauer supernova is like roughly 30% of the total effect of turbulence. That's what they find.
So, a few more questions. So,
Okay, two short questions.
Yes, Tower.
One is just a clarification. The advective sound waves, is this basically a cavitation process?
What is gravitation process? I don't know.
You're forming basically collapsing bubbles in the fluid?
In a sense, maybe yes. In a sense, yes. So let me try to explain. At least the way I understand it. I don't fully understand it. So suppose you have a temperature perturbation right here. And suppose this is in pressure equilibrium. You have higher temperature in pressure equilibrium here. And this is being advected. But if the flow is converging, that pressure equilibrium will be violated. That pressure equilibrium violation has to settle, right? And that generates sound waves. That's the way I understand it. And you can calculate it analytically also.
But are the sound waves linear or they go through a nonlinear?
It's a linear coupling. It's a linear.
It's a linear.
Yes.
Okay, so not cavitation. The second question is in the 3D modeling, is there rotation in there?
Okay, so in this model which I showed, there is no rotation. There have been some pioneering attempts to include rotation in simulations, including by our group at Caltech. We know very little about the effect of rotation. So as I said, there is effects through magnetic fields. We did first three-dimensional simulations of Krakauer supernova with magnetic fields, and what we found is that when you are trying to form jet, it becomes m=1 unstable. So jet wobbles and it gets destroyed. So we couldn't see explosion, even when we have very strong rotation. But again, it's a magnetorotation turbulence. It's not fully included in our simulations. We have very approximate model for that. If you include everything, who knows, maybe we'll get it. So that's the second thing, that people include some mild rotation, and they found some interesting non-axisymmetric hydrodynamic flows.
Right.
Which I don't understand.
Right. So the reason I ask is because not for core collapse supernova, but for thermonuclear supernovae, people, I don't think they've fully demonstrated it in 3D, but the idea is the rotation gives you a shear instability in the density structure, and you get these instabilities, and that entrains some of the internal energy, and that helps the shock move
Exactly,
out.
exactly. So that's the idea. That's, I mean, people are trying to see it in simulations. Again, in our simulations, we don't capture the turbulence. We approximately put it, and what we see, we don't see strong jet. Jet gets destroyed. There is, yes, more work needs to be done in this area.
Show please the model of your star, the number of shells.
Okay.
When we are talking about the shock waves, it is easy to understand that. Look at me. Let's consider any in a shell, and it radiates not only inside but outside also. And if we are considering more higher shell, and it radiates also inside and outside. Look at me. My question is, maybe radiation from outside of lower shell may be depressed or absolutely coincide with radiation of upper.
Okay, so let me understand your question. So you're saying is that, so suppose you have this outer shell, right? So you're saying that outer shell emits radiation and that gets absorbed by the shock. Is that what you're saying? Am I understanding you correctly?
No.
Okay.
No. Every shell radiates inside and outside.
Okay, okay.
So that is why we are considering two shells. For example, this shell radiates inside.
Neutrino radiation or
inside.
photon radiation or neutrino radiation?
What?
Photons or neutrinos? What radiation? Photons are negligible because it's optically, this is optically thick, this is not opaque. Photons do not propagate inside the star. Neutrinos, okay, neutrinos can propagate, but neutrinos due to this nuclear burning is tiny compared to what neutron star is emitting. It's just nothing. No, I wouldn't say so. It's not an important effect.
Your viewpoint, this is a question that necessary to consider more detail.
Well, it has been considered, and it was found to be not to be important.
Try to do it, because it is very.
Okay. Okay. Yeah. Can I interrupt you for 1 second? So, it's a question to organizers. I just wanted to say a few words about the physics department, just to give you numbers, how many faculty, how many students, and so on and so on we have. Shall I do it right now? I just need 30 seconds, or shall I do later during?
So we have round table.
All right, during round table, I'll be first then to discuss that.
So we have the last speaker, and then.
Okay, thanks.
Yeah. So let's thank the speaker again. Yeah. Thank you. So thank you very much for the lively talk. So our next speaker is Ayjan Murzakul. So, okay, let's start.
How do I talk? It's switched on. Хорошо, я вот так. Okay, good afternoon. First of all, I would like to thank organizers for this conference. Today's my presentation topics is thermodynamics of ADS black holes as regularized with delta susceptibility. This work was done by Professor Daoud Momeni, me, and other collaborators at Eurasian International Center for Theoretical Physics at Eurasian National University. So you can find this paper on arXiv with the same title. So my presentation is organized in the following way. So first of all, in introduction, I'll give briefly definitions of quantum information quantities such as entanglement entropy, holographic entanglement entropy, fidelity susceptibility, and holographic complexity. So in the main body of my presentation, I will apply this holographic quantum information quantities to Reisner-Nordstrom anti-de Sitter black hole. So before giving definition of entanglement entropy, let me introduce you a concept which is called entanglement. So entanglement is a property of two or three quantum systems. So let's consider two systems with corresponding Hilbert spaces, and the Hilbert space of a combined system will be a direct product of these two Hilbert spaces. So we say that these two systems are entangled if the system cannot be expressed as in expression number 1. So if we have two particles, it means that each of these particles will have two different states. For example, let's consider z direction. So in this z direction, one particle can have spin up, and then other particle will have a spin down. So in other words, the expression 1 can be written as an expression 2. So this state is not entangled. So we can check it by find entanglement entropy for this system. In contrast, the system, the quantum system as expressed in expression 3 is entangled. Again, it can be found by finding its entanglement entropy. So actually, this state, expression 3, is very well known as an A-pair pair in quantum mechanics. So A-pair stands for stands after Einstein, Podolsky, and Rosen. So it's already very well known that expectation value of operating quantum mechanics are found as an expression 4. So this state is described as, by a density matrix. So using expression 5, we can rewrite expectation value for an operator as in 6. So if we can write density matrix as in expression 7, it means we're dealing with a pure state. So now let's turn to the definition of entanglement entropy. To the definition of entropy. So in classical physics, entropy is defined as an expression A. This in information, not in classical physics, in information theory, this entropy is called Shannon entropy. So if we multiply Boltzmann constant to this entropy, we'll get a Gibbs entropy, which becomes more physical. So in quantum statistics, entropy can be found as an expression 9. This entropy is called von Neumann entropy. So if we are working with reduced density matrix, it means if we take a partial trace of a system, then we can rewrite von Neumann entropy as an expression 11. This entropy is called entanglement entropy. So before giving definition of holographic entanglement entropy, let me introduce you a holographic principle. So it's well known that information inside of black hole are expressed by entropy, and this entropy is called Bekenstein-Hawking entropy. So here J is a gravitational constant. So, so degrees of freedom in gravity are proportional to the area of a black hole instead of its volume. So holographic principle was first introduced by Gerard T. Hooft and then developed by Leonard Susskind. This principle says that D plus two-dimensional gravity theory is proportional to D plus one-dimensional non-gravity theory, such as quantum field theory, conformal field theory, quantum matter, and etc. So an explicit example of such holographic principle was introduced by Juan Maldacena, and he found the correspondence between ADA spacetimes and the conformal field series. So nowadays, one of such well-studied example is correspondence between five-dimensional ADA spacetime and the four-dimensional conformal field series. It's very well studied example. So now we can introduce a new concept, holographic entanglement entropy. It was proposed by Ryo Takayanagi, and it can be found as an expression 14. So we see that it looks almost the same as Bekenstein-Hawking entropy, but the difference is that here, in this case, in holographic entanglement entropy, we use a minimal surface. So let's move to the definition of fidelity susceptibility. This concept was introduced by Susskind and also by Alyosha Hiha recently. It can be found as an expression 15. It means that fidelity susceptibility is proportional to the volume of the bulk and to the maximal volume of the bulk. By bulk, I mean gravity. We have bulk and the boundary. Let's consider n-body quantum system with Hamiltonian as given in expression 16. So let's assume that this Hamiltonian corresponds to the pure state. So if we add, perturb our parameter a little bit, for example, lambda parameter, so our Hamiltonian becomes as an expression 17. So our perturbation is very small in comparison with the Hamiltonian of a pure state. So this concept fidelity susceptibility was introduced by Susskind and Alyosha Hiha in quantum information theory. However, the concept of fidelity is already exists in condensed matter physics. So this fidelity can be found as an inner product between two infinitesimally different quantum states as an expression 18. So 18. This G lambda lambda in this case is called fidelity susceptibility, but this metric itself is called fidelity. So the next holographic information quantity is holographic complexity. It was also proposed by Susskind recently. So it means this definition says that holographic complexity is proportional to the minimal volume of the bulk. So the difference between holographic complexity and holographic fidelity is that in fidelity susceptibility we use maximum volume of the bulk, but in holographic complexity we use minimal volume of the bulk. So let's move to the main part of my presentation, which is Reisner-Nordstrom anti-de Sitter black hole. Its metric is given as an expression 21 with a function of p given as an expression 22 with small parameters epsilon and delta, delta as shown in 23. So we find we try to find this relation in this section. We'll try to find the relation between holographic complexity, fidelity susceptibility, and the thermodynamic volumes for Reisner-Nordstrom anti-de Sitter black hole. So in order to do that, we first of all find the area enclosed area in a region of black holes. So it can be found by expression 24, which is already known in general relativity. So our Lagrangian is given as in 25. So the Euler-Lagrange equation, which corresponds to this Lagrangian, is given as in 26. So you see that it's quite difficult to calculate it analytically. That's why we used Maple in order to find these expressions. Then we find from this second order differential equation, we find black hole radius as an expression 27. So after some mathematical steps, we use this radius and insert it to the definition of entanglement entropy. So we first of all find the entanglement entropy for pure ADS spacetime, and then find calligraphic entanglement entropy for deformed ADS spacetime, and we take we contract them from each other. So the Lagrangian is found as in 26. So we integrate it. After that, we find after finding area, we find a volume and a complexity volume and a volume corresponding to fidelity. So they look almost the same. So after it's difficult to calculate these integrands. That's why we expanded in Taylor series. So after expanding in Taylor series the integrand, so our expression becomes as in 20 as 35. So the mass and temperature for resonant Nordstrom black hole are already known. We just use the facts. Actually, I didn't write the expression for pressure. I mean the result after the inserting this definition, because it's very long. If we solve the expression number 37 in terms of a black hole horizon, we get fourth order polynomial as an expression 39. So the roots of this equation are given as in expression 40. So using known way of solving fourth order polynomial, we find the roots of this fourth order polynomial, but we need to find which of them. We need to find the largest root of the largest root of this equation, which corresponds to the outer horizon of the black hole. So this here the coefficient k is expressed as in 2045. So we see that the expression under square root should be bigger or equal to 0 in order k to be real. So we solve this inequality and solve it for temperature. At the end, we find that the maximal temperature we see from expression 49 that maximal temperature will be when Q charge will equal to 0. So it can also be seen from a graph. So if we can't solve it analytically, we could solve it graphically. Okay. Let's find a black hole, the Reisner-Nordstrom anti-de Sitter black hole horizon. In order to do that, we need to solve. Sorry, this expression equations numbers are not written. We need to impose a horizon condition in order to find black hole horizon. So we write this our previous fourth order polynomial in terms of 51 in terms of new function xi, which is just r divided to ll. Here is the radius of the ADS spacetime. So again, analytically, it's not possible to solve this fourth order equation. That's why we use Maple, but with Maple it also becomes very difficult. That's why we used a little trick. We used a graphical method, but this method is not just a usual method. We use a little trick. I can show you exactly how to do it after the session if you are interested. So this trick tells us that we have to plot 4 graphs, 4 cases. So as soon as you find one positive root, you don't need to look for other roots because other 3 of them will be negative automatically. So we found in the first graph that the root will be negative, in the second graph the root will be negative, and in the third graph the root will be positive. So we didn't calculate, we didn't draw the fourth graph because the answer is a third root. So now if we draw a graph of relation between pressure and the volume, thermodynamic pressure and the volume, we get this figure number 3. If we draw again the relation between fidelity pressure and fidelity volume, we get almost similar graph. So if you compare the previous graph with the second graph, they look almost the same. So, however, if we plot the graph of relation between complexity pressure and the complexity volume, the behavior is totally different. So it's as expected. So it means that complexity measures the difficulty of connecting 2 different states. So that brings to the conclusion. So this topic is a relatively new topic. That's why lots of cases needs to be studied. And however, what we are interested at the moment is first problem is finding holographic intangible entropy for non-ADA space-time. So we people consider ADA space-time because it's only nowadays space-time which is compatible with the theory. That's why people consider ADA space-time. But what happens if we try to find holographic entanglement for another space-times? So the next question is what is the analog of the Einstein equation for this holographic entanglement entropy? And the third, but the most significant one is maybe the question: does this quantum entanglement can explain quantum gravity? So that's the end of my presentation. So if you have questions, I will be glad to answer them.
Questions? Yeah, sure. Michael, good. Yeah.
Yeah, I'm curious if you did this for the Kerr case. Did you try that already, or has it already been done?
Sorry?
The Kerr case with a rotating black hole.
Kerr black hole. No, actually, in this work, we did it for Schwarzschild anti-de Sitter black hole, for Reitner-Nordstrom black hole, and for Schwarzschild anti-de Sitter black hole in any dimensions. We didn't consider Kerr black hole because this paper gets so big and the calculations get so cumbersome.
Okay, so you picked the Reisner-Nordstrom because it was a more simple case to start with.
We actually started from Schwarzschild anti-de Sitter black hole, and then moved to Reisner-Nordstrom. Maybe Kerr black hole would be our next paper.
So, any more questions? Well, where? I don't see. Okay, good.
The temperature of your anti-de Sitter black hole could be negative, you show us. Has it some physical sense or not, or you have some restrictions?
Our temperature is negative.
So just algebraic algebraic relations show us that the temperature could be negative.
Well, temperature could not be negative. It can be from 0 to 0.27567 and so on.
No. As I remember, 17 transparency. You show, T is a function of Q, and for the graph is confined.
Yes, we insert the condition that Q should be less than L over 6. L is the radius of ADS spacetime.
Is this some physical meaning or not, or just your restriction?
No, we find this restriction by calculating some. At some point, we use it can arise from our calculations. We didn't impose it from outside.
Okay.
So, no questions?
Okay. Angle theta. What is this angle theta?
Angle theta.
Show the first slide. First, second.
This one?
One. I don't see here. Where is theta?
In 2024.
For example, theta. What is this? Physical essence of theta. Angle theta.
Reisner-Nordstrom.
This is polar angle, isn't it?
Yes, R, theta, and phi are
spherical coordinates. Yes. But look at me. When you said that you have decomposed with respect to angle theta, but in this case, if you are decomposing, you mean that theta is very small. If it's so, the trajectory will be almost straight line. And how it is possible to compare your results, this conclusion with your results? You see?
Not quite. Could you explain? Okay.
So okay. Then, no. If there are no more questions, so let's thank Ejan again. So I announce that this afternoon session is closed, and we have the round table, and okay, so you want to present something?
Just one slide,
sure.
10 seconds. Okay. I just wanted to use this opportunity and to say a few words about the physics department at Nazarbayev University. We have a 13 faculty. Who are here. Most of us moved here 2 or 3 years ago. Most of us from Western universities and institutes. And I just wanted to give some few numbers for the perspective, just few numbers. Okay, so we have in this university what is known as oral proposals. It's a competitive proposal where we propose some scientific research, and these proposals are sent to the US for peer review. Each proposal is reviewed by 3 independent researchers, and then according to the results, we get approval. So physics department has 6 proposals approved. Doesn't mean that we got the money. We didn't get the money most of the time. We got 6 proposals approved. This number, we have 13 faculty. This number is almost a third of all the oral proposals approved to the entire university. Okay, we have 300 faculty. 13 of us, we have third of all the proposals approved. That's the first number. Second number I would like to mention is that last year we had a first cohort of our undergrad students graduating, and most of them are now in top universities. Most of them are in the US, including top places like MIT. And related to this number, last year President Nazarbayev handed 10 diplomas to top universities in these universities. Okay, almost half of those 10 universities, entire universities, were from this department. Okay, and finally, I would like to mention this H-index, average H-index of each faculty member, summed and divided by the number of faculty, and this is 17. It is low number. We are young researchers, but this is the highest in Central Asia. Okay. So in other words, according to this number, physics is the strongest science. Physics department, physics is the strongest in Central Asia. Okay. I would like to. I just wanted to mention that. Thank you. Okay. So I will. Oh, okay.
So I think thank you for this very important information. So I hope. So yeah, what do we do next? Take photo. Do you want? Does anybody want to say something? Final words or some before the round table? Okay.
Okay, so we have a roundtable today and another one tomorrow. Um, what I think is a good way of doing this is if someone from each of the institutions within Central Asia gets up and gives a 1 minute description of their department, what types of research are going on. And then at tomorrow's roundtable, we want to look for collaborative um, ventures between us. So we heard, for example, that there's gamma ray bursts going on at Maidanak Observatory and at in Tianshan Observatory at Almaty, and they don't really know about each other. So we want to hear all the different types of astrophysics that are going on in Central Asia to try to get these networks going and try to get common areas of interest. But first, let's just sort of pass the mic around. If you're from an institution in Central Asia, if you can just give sort of a 1 minute summary of what types of research, how large your department is, and so forth. So let me just start. Well, we can start passing it along here.
Well, I can start, but probably tomorrow I will be more ready because I have no presentation now. I just let me introduce myself. I am from Kazan, and it's not Central Asia. It's I don't know. It's Russia, so maybe it's Europe, maybe Asia. I don't know. Maybe it's really center. Okay. Okay. So let me prepare some short presentation for tomorrow, and now I will be very, very short. I am from Kazan. Kazan is a city situated on the Volga River, and maybe you know Ulyanov Lenin, great politician and great Russian Revolution, which happened exactly 100 years ago in 1917, last century. And so Lenin was our student of Kazan University. But this is history. More ancient history is connected with name Lobachevsky. Probably some theoretics know this name. It's and we are working in curved space-time, and Lobachevsky geometry was the first non-Euclidean geometry in the world. What about modern condition? So Kazan University is great, one of the greatest university in Russia, and the physics now it's not department. The name of our department is Institute of Physics, and we have a lot of various directions. But what is interesting for this auditorium is it's a department of theory of gravity and gravitation. I'm head of this department, and this department was founded by the other famous person, Alexei Petrov, again, who is working with some mathematical aspects of general relativity knows the classification by Petrov. So he was a founder and first head of our department, and we are working in various aspects of gravitational physics and also mathematics. And as a part, also we concern the quantum field theory on curved space-time. And also maybe for especially for tomorrow, I will present some astronomical direction of our university, because we have astronomy department and we have very nice facilities, and we have a telescope 1.5 meters telescope in Turkey, so nice climate there, and our astronomical group is involved in Planck project. Now it's also working in maybe you heard spectral gamma, spectral Röntgen gamma project, and it's very impressive project, and just in this direction, as you said, it's very important to well provide a connection between gamma observations and optical observations. So our group is very intensively included in this project as a optical support of this project. So it's very interesting. I think it's very interesting to find some points of intersection, and maybe some points for further collaboration. So personally, I am working in cosmology field mostly, also wormholes, black holes, quantum field theory, and also Casimir forces, and so very in some times ago it was extremely interesting for me to construct some models of wormholes, because you see, I mean, Michael knows very well that quantum fields violates all energy conditions, and so is it really physics or not? It's up to now it's not clear, and so it's point for discussions, and a lot of people discussed this problem, but nobody, there are no it's not clear is it physical or not. So well, let me give some presentation with numbers, how many students, how big. I am not ready, frankly speaking. I am not ready to do it. If you are interested, I can answer your questions. Yeah? Okay. Just one remark. I forgot. And actually, again, not today, tomorrow, I will show you some announcement. The matter is that each year we organize so-called Petrov School. This is conference, a school seminar. Actually, there are two parts. One part is it's really a school for not for only students, for younger people, for young scientists, for students, postdocs, postgraduates, and so on. And this November, 27 November, from 27 to 2nd December, we organized traditional Petrov School. I give you general information and invite all of you to this school. And Alexei Stravinsky, he is president of this school, and it's a traditional school. So it's yes. This school is organized by Kazan University and Russian Gravitational Society. So, okay.
Thank you very much, dear colleagues. Of course, I say a few words about our institute, about our astrophysical institute. First of all, because astronomy have the long history in Kazakhstan. It's about more than 70 years. Last year we celebrate 70 years of our institute. I remember that uh, I must say that the founder of our institute was the famous Soviet astronomer academic Fesenkov Vasily Grigorьевич, corresponding member of Academy of Sciences, Soviet Academy of Sciences, Gavril Tikhov, and some other famous persons. Now I want to resemble you about one of the famous Kazakhstanian scientists, astronomer. This is Professor Ridlis Grigory Moisеевич, who put forward first in the world the so-called anthropical principle. I must resemble you that from what is the physical essence of anthropic principle. He said that people, men, may live in time interval plus 70 degrees, minus 70 degrees, and you see the temperature in our Earth becomes larger and larger and larger. Maybe this is the result of changing the anthropical principle. Who will know what will be later? But nevertheless, this is very important. What about our other scientific directions of in our institute? First of all, this is cosmological searching. We developing the numerical astrophysics. We developing the physics of galaxies, physics of stars, physics of nebulae. Of course, one of the important parts or directions in our institute. This is searching the in different aspects of the solar system, and of course the satellites. I hope about some of these directions we will say you maybe tomorrow or more later. As Professor Sushkov said about the conference devoted to jubilee of Professor Petrov, in this year we also make the fifth Fesenkov's readings. They will be in Astana also, and of course I'll send all of you our invitations to take part in this conference. And the last point what I want to say that we have a number of telescopes, and we are planning to construct, to put in near Almaty the principally new telescope. For when I talk about the principally new, this means for Kazakhstan. This is telescope sizes of in diameter of mirror about 3.6 meters. This is very interesting. This is very important and for us, and we hope that by this telescope we'll get more famous results than before. And about some international contacts between our institute, I must say that we have direct interactions with Heidelberg University, Heidelberg Astronomical Institute, also with Korean KASI, of course with Russia, astronomical institutes with Russia, Academy of Sciences, and so on. That is why, of course, my presentation, this is not presentation, this is only brief information for you, for those of young students whom I see today for the first time. And I hope that we'll, in future, we'll develop our contacts more and more, and we'll find wonderful as theoretical and observational results. What? About conference? Yes, I said about the fifth Fisenkov's readings. Fifth, they will be in Astana, but I don't know where it will be. Maybe it will be in Eurasian Institute, or maybe in other place. Now it is not known, but we'll try to do it. And don't worry, I'll invite you personally, of course.
Thank you very much.
And of course, with marking the address where you must be.
Or maybe let me say a few words. Well, I'm in a little bit special position because my permanent place of work is the Landau Institute for Theoretical Physics, and it is not related to any specific university. And our style is just because we have about 60 members who cover, I would say, practically all areas of theoretical physics, and that's why practically all our members of our institute has also part-time positions in many other places, in particular both in Russia and outside, and that's why indeed many people like me actually have groups and with well-known scientists and young scientists in many other places. So speaking in particular about me, so in addition to, as I said, to my position in the Landau Institute, also I have a large Russian grant on modified gravity with Professor Sushkov, and so actually the main part of young people who works in the scope of this grant is in Kazan University, but also I have a group of my former students in India, and students of my former students, like students of Professor Varun Sahni in Ayuka in Pune, and also his student, and so in some sense my grant student Arman Shafilov, and in particular also that's why we also have some joint activity with Professor Smut and Arman Shafilov in Korea, so some group in Korea too, and also one more member of our institute, Professor Kamichuk, who is also now he has a permanent position in Bologna University. So that's why with him we have now a group in Bologna University too. And so that's why I would say I have a rather wide field of activity. So let me indeed only mention some very recent changes. First, we have our people from Balandau Institute. We are now we have organized a new physical department for for students in some institute which uh, uh, educational institute which has the name. So it's a kind of école normale in Paris. That is called higher school of economics. So it was it existed with institute existed for many years, but now they decided to organize a physical department, and actually members of my institute, in particular me, we are now organizing this department, and it has this institute has money, has some special money due to its, I would say, good relation with Russian government, and in particular, it has a possibility to for foreign students too. And second, speaking about conference, just this year I accept that I was elected the president of the Russian Gravitational Society, and we're organizing many conferences. So, in particular, in addition to that conference, which was mentioned by Professor Sushkov, we also have large conferences, large they called Russian Gravitational Conference, but they are also international too. But this conference are rather large, so they organize once per 3 years, and the last conference was only a little bit more than a month ago. And so I would like, indeed, maybe if you have, indeed, if you have some kind of society of some Kazakhstan, people working in general relativity and cosmology, I will actually I think is and also I will be interested that we may make some agreement about collaboration in future.
Can I show you announcement? So it's necessary to. I'm a lecturer with about 40 years, so I have very loud voice. So actually, just for your information, and I have already resent this information. So I just it's not specially for this event, but I if I obtain some email addresses of you, I send you also, and it's just first information letter, and it's winter school. Actually, it's actually winter school because November in Kazan. Last year, some guy from Vitória, Brazil, came to Kazan and was extremely happy because he seen the snow first time in his life. I prepare for him warm clothes. So, but everything he was safe. Don't worry, and he is alive. Yeah. This is you see preliminary list of lecturers, and I think that something will be changed and new names will added. But you see, Strabinsky, Professor Bikmaev, he is head of this project of Kazan part of project Spectre Rentgen Gamma. Fabrice, professor from Brazil, Professor Mustipanenko, he is great expert in Casimir, and actually maybe greatest expert in Casimir effect. Klimchitskaya, she is his his wife, sorry, and maybe you know the name Salvatore Cappucciello. Chervon, our friend from Ulyanovsk city, Volkov, and so some other guys. Maybe some names are known for you. So I will send you this information, and you are welcome.
Okay. Thank you, Sergei Shkov, Professor Shkov. And firstly, I would like to thank our chairman, cannot by God, but he's not here, Mikhail. Thank you for, sorry, Professor Kavanis also was chair at these sessions. And this is my first announce about the dinner. It's my pleasure to invite you dinner, which will be at and I think it's 7 p.m. where the coffee break place. So please, we will be waiting you. Okay. And see you tomorrow at 9 o'clock at the same place.
And
Bus will be waiting you like today.
and let's thank organizers Alia and Misha for excellent organization.
Yeah, and also our guys, engineers. Thank you, guys. Good job.
I'm sorry, I forget something. Yes, sorry. Now we need to make this photo, big photo for next time. Okay, so.